Hello. Here, as an exercise, we will investigate, or rather describe, all integer points on the parabola given by this equation. So that's the task, to find all integer solutions, all pairs of integers x and y, which makes this equation true. The key step in solving this equation is to get rid of one variable, the linear variable y. We can get rid of it. Oh, let me make it more interesting. Let me make it a composite number, not just 5 but 15. That will make it more fun. And the way of getting rid of it is to replace the equation of integers by the congruence. So my first claim is to solve this in integers x and y is effectively the same as to solve this congruence in x. So I'm considering now my integers modulo 15, which make this disappear. And then what I'm left is with are these two terms, and I'm arranging them on different sides of the equation. So now it becomes an equation that multiple of square is something else. And that equation is way easier to solve, at least to determine when it is solvable. And then we can find all solutions. So jumping ahead, the set of solutions of a solvable parabola, solvable in integers, will consist of a union of arithmetic progressions. And these arithmetic progressions, sort of the seeds for them, will come from solutions to this equation, to this congruence. And this congruence could have, well, some number of solutions. For odd moduli, this number of solutions is always a power of 2. Well, actually it's always a power of 2. But for odd moduli we can really determine quickly what is this power. The power is really the number of different primes inside our modulus. And let's see how it comes about. So now we have this congruence at hand. At least solvability of it is the same as solvability of this. And actually, any solution, xy, integer solution of the original parabola, if we just look at x components of it and reduce it mod 15, it will be one of the solutions of this congruence. So we are not losing anything by reducing down the congruences. But again, congruences are easier to solve. Our modulus is a composite one, so now we can replace one congruence modulo 15 by two congruences modulo the prime factors of 15. It will be the same algebraic expression, but now we're considering it mod 3 and mod 5, which are the factors of 15. And now we have to solve these two congruences together to get an equivalent condition on x. So these two we can simplify, rewrite into x squared equals something. So here 7 mod 3 is 1, already have x squared, and negative 2 is as good as 1, so really that's what we have. For modulo 5, 7 is the same as 2, and we have negative non-s, so we can cancel that out. And that way we have x squared congruent to negative 1. Negative 1 we can also replace by 4 rather, which is the same modulo 5. So now we have this system of congruences, and we know the solutions. So the first is solved by plus or minus 1 modulo 3. The second is solved by plus or minus 2 modulo 5. So these are all equivalent conditions on x. And now we just have x as a member of arithmetic progressions with a step of 3 or step of 5. Now we can combine these two and find x's modulo 15. After all, we have to solve this congruence modulo 15. And yeah, well, we'll just start with writing x as, well, I'll choose 1 first, as 1 plus some multiple of 3, and then I can use the second congruence to determine what the multiple is, so that I will see all possible solutions modulo 15. And what I know that if I take this template of a number and reduce it mod 5, then it should be plus or minus 2. So let me just write plus or minus 2 being congruent to 1 plus 3u modulo 5. And now some simple manipulations. 3 is the same as negative 2, and put on the other side it will be just positive 2, and then I factor 2, and I'll have u plus or minus 1 on the left, and what is left on the right is just the 1. So to solve it, to simplify it, I can cancel to divide by 2, put it on the other side. The inverse of 2, which I need to multiply both sides, is 3. So that I can rewrite, u plus or minus 1 still congruent to 3 modulo 5. And finally I get my u. So 1u is when I take plus and subtract it from 3 and I get 2. The other is when I get negative 1 and then I put it on the side, I add it to 3 and I get 4. So u really is either 2 or 4 modulo 5. Plugging it in this template, I have my answers for x at least modulo 15. So if u is 2, I have 1 plus 6, that is 7. And if u is 4, I have 1 plus 12, which is 13. And these are the remainders modulo 15, corresponding to two possible solutions. So in total, just to come back, what we have here is two possibilities for x modulo 3, two possibilities for x modulo 5. Combined, they have they give us 4 solutions. So here we have 4 solutions. Each of them generates an arithmetic progression by shifts of 15, and then knowing x, we should be able to determine y, because they should be a solution. And these will be 4 arithmetic progressions of integer points on the parabola. So 4 arithmetic progressions will be in the x-coordinate. We already found 2 of them for choosing x to be 1 modulo 3. Now we can continue and find the other 2. The template will be this, and then all the computations I had are going to just change slightly. So then again, putting on the other side, it's the same trick, replacing 3 by negative 2. I'll have this, but then I have negative 1 on that side. So again, dividing by 2. Oh, made the same mistake again. I have now negative 3, which is 2. And now if I compute what u is for plus or minus sign of mine, it will be either 1 or 3 modulo 5. So now I'm seeing the answers for x for these 2 values of u. When u is 1, I have negative 1 plus 3, that will make 2. And when you use 3, I have negative 1 plus 9, which is 8. These are the remainders of my x modulo 15. So these are the two other arithmetic progressions for my x's. And the first checking point, solutions come in pairs. We can take x, we can take negative of a solution, still be solving the same congruence. So look what happens if we take negative 2, modulo 15, it will be 13. Negative 8, modulo 15 is 7. So indeed, these are just the negatives of each other. Now we can really just solve for these two. And writing it in integers as a member of this arithmetic progression, we could find the y. Now we are guaranteed we're supposed to be able to find the y. That's checking point. So what do we know about y? 15 copies of y supposed to match with 7x squared plus 2, right? That is just the original parabola equation we're solving. And now we have this template for x. We just plug it in and do some algebra cancellation and see what happens. So we have 4, then we have 4 times 15, I will write it as a product L, and then we have the square, I will write it as a 15 squared times L squared, and then all it plus 2. So now these 15s are going to be cancelable with this 15, so I really need to see a multiple of 15 on the right hand side to get my y. So the key point is to take the product of 7 and 4 and to add 2 and to hope for the best that this is divisible by 15 as well. Well, 7 times 4 is 28. With extra 2 it is 30. That is twice 15. So in total we have 15 throughout our expression. I am combining this and that into 15 times 2 and factoring 15 from everything, which I can now. And then what I have left is 4L and then 15L squared. So we'll just write them as they are. 4L plus 15L squared. That's what I have. And that gives me y. Y is just that number, 2 plus 4L plus 15L squared. So this is the first arithmetic progression corresponding to the remainder 2 for the x coordinate. Well, for the remainder negative 2, which is the same as 13, I can just flip the sign in here for the whole x and keep the same y, and that's supposed to solve my parabola. So that is x being negative 2, negative 15L. This is the first sequence of solutions, y being just the same. The other two, the remaining, are corresponding to 8, to x congruent to 8 modulo 15, and the story of determining the y-coordinate is the same. So if we now write this template, we have to compute what y is in the very same way. So we take 7 copies of the square of this x, which is, I'll just write it as 8 squared plus 16 copies of 15 copies of L plus 15 squared L squared, still plus 2. And again, that should be all divisible by 15. So this plus that, please check it out, is 450, which is 15 times 30. And then factoring 15 out from these two terms, I have 16 copies of L plus 15 copies of L squared. So this time the corresponding y-coordinate is given by this formula. And that is the arithmetic progression with this remainder in x-coordinate. And the negative version of it, or the remainder 7, is when we just, again, flip the x sign, but keep the y the same. So this is a complete list of all possible integer points on this parabola. You could check, of course, that these points really solve the equation, but moreover, any solution will be one of those, and these solutions are all different. So that's it. See you later.